Everybody, welcome to lecture 5. So today we will learn into learn into long day. So let me rewind back. So today we will learn about residual neural networks, and basically these are neural networks that are very popular in deep learning, and we will discover the story or the rationale behind the design of these residual connections, or what we call skip connections. So let's start with reminding you guys of the structure or the architecture of a simple neural network, such as a fully connected network or a CNN, an MLP. So all of those are processed, or they operate in a sequential manner. So what does that mean? It means that first we have an input data. So this is our input data X, okay? And this is our target. This is the goal that we want to hit. So we want to predict the Y. So to do so, we pass the output of each layer directly to the next layer. So let's start with the first input. So the first input is X. So we pass X through the first layer, F1. So here, F1 is the learning mapping of the first layer that we want to estimate. And we learn F1 by estimating W1 hat and B1 hat. So W1 hat is the linear transformation or aggregation of our input features. And we add a bias over here for any distribution shift that we have in the data, for example. So we repeat that. So once we get the output H1, so H1 will be here. Now we feed H1 into F2 and we estimate the parameters phi2. So the parameters phi2, they parameterize the transformation F2, and this would be composed of W2, the weights of the linear combination, plus a bias for this layer, okay? So here we do the same. So you can see that now we're feeding H1, we're passing it over to the second layer, we're outputting H2, we get H2, the new hidden representation that we're learning, and then we're passing it over to the next layer, F3. So, and it's in a similar way, we're going to keep doing this until we get to the very last, layer where we get H4, and H4 actually is, is almost equal to Y. So we can have, for example, a simple activation function there, or softmax, to transform the final, elements in this hidden representation at H4, apply an operation here, and then we're going to get the Y. So here, for the sake of simplicity, we'll say that our output is actually H4. Okay, cool. So now, this is done sequentially. Okay. So one thing about this network, when you train it sequentially, is that you may not have only one single path to get to Y. So we have seen that we need to identify or to learn the phi 1 and phi 2, phi 3, 4, etc. All these hyperparameters of our network of these sequential transformations. We need to optimize the loss function. So if we optimize the loss function, we will get basically a path, and this is, for example, a path that transforms X onto Y. So here, if we write it down, we can write F total. So this is the total path of X is equal to Y. It outputs Y. Now, if we change a little bit the data set, or if we initialize the parameters W and B differently, if we initialize these guys differently, okay, then we're going to end up with a different pathway. So here, we will have another, for example, shape, and it's complex. It's something like this that connects these. So this is another F total that we got by changing or the initialization of the model. So this solution basically is very sensitive to the way we initialize the model parameters, to also the distribution of the input data. So if we want to identify if this is a cat, so we need to look at the distribution of cats in our data, but this may not be universal because the real distribution may look like this, okay, for example. So we're always taking a sneak peek at the data distribution because we cannot see it all. So remember, guys, in the machine learning course, when we looked at the distribution of, so let's say, for example, this space right here represents the distribution of all cats in the world, like the images of cats, and this one represents the images of dogs. Okay, so I'm just taking this space to draw. And when we are training our models, we have only a sneak peek at the data. So we collected data from this part of the manifold, and here from a different part of the manifold, and you can see that this has a particular distribution, and this, class also of training samples had a particular distribution, but it's not universal because we're only looking partially at the possible observations or manifestations of what a dog is and what a cat is. So anyways, it depends on so many things. Distribution of the data is a key word, okay? So the word here, distribution of the data, so this depends, these paths, they depend, or the paths here, the final solution or the network itself, the trained network, depends on the distribution of the data of the train set, okay, and of course, each class, and also of the initialization of the parameters across all layers. Okay, so how are we going to initialize those? Okay, now this is how we have written this function before. So if we want to write it as a series of nested functions, we will get the f total, that is a composition of a bunch of consecutive or sequential tiny neural networks, okay? So one layer network concatenated with another one layer network, another shallow network, one layer, etc. And when you stack all of these, when you compose them, you stack them in terms of architecture, you compose them in terms of functions, okay? We're gonna get the total transformation. So, and you guys can write this very easily, so I'm just going to clarify it a little bit here. So the F3 takes the first element. So this is, the transformed element from the previous layer F3. And these are the parameters of our function F4, okay? And then when you look at F3, F3 takes as input the output of layer 2. So this is layer 2 and its parameters here. And now layer 2, it takes basically as input the output of layer 1, okay, with its parameters phi2. So you can see the nestedness. It's like a pyramid. So now, one thing about this, there are several issues that come with this sequential training, different issues. And we're going to look into two issues today. So the first one is the deeper the network gets, the harder its learning becomes, okay? So as we want to add more and more layers, so we want to add F5, F6, F7, etc., the training of the network becomes harder, which means we struggle at making the training or the loss on the training data decrease. So we have a bad behavior of the loss on the training data. So let's look at this example, this graph together. So we'll start with this graph. So in this graph here, this is basically a 20-layer convolutional neural network. It's a CNN. It outperforms, you can see that a 20-layer network here, in terms of test error, it has a lower error compared to a 56-layer network, okay? So during the training, when training the model, when we test it on the unseen data, so here, so I'm gonna use a different color. So when we test it on unseen data, okay, on the test set, we notice that the 20-layer model, it has a better performance. So this is much better, much lower error compared to the 56 layer. So here, this is, by the way, on the Safari 10 data set, and it was published in this paper. Now, let's look at another example here. So in this graph, now we're looking not at the testing error. So first, when you look at this, you may say, maybe the problem is actually in the test set. So maybe my model, my 56-layer model, my deeper model, it struggles to generalize. Basically, it struggles to generalize to unseen data. But this may not be always the case. So we need to check the error of the training to see whether it's struggling to generalize or is it struggling to learn. Is it struggling to learn or to generalize? So here, obviously, it is struggling to generalize to unseen data because you can see that it has a higher error, the blue curve over here. But let's see what happens when we look at the training error. So this is the training error. And this is our, so I'm going to use a different color. So here we have our training, our testing, our 20-layer network. This is the training error, the training loss of our 20-layer network. And we plot the loss of the 56, the deeper network. What do you guys notice? First, you always have a higher error for the deeper network. Okay, so the deeper network is not being trained well. And this is clear here. So now we know that we have two problems, that the network, the deep net, okay, struggles to learn. It's not learning properly because it struggles to decrease its loss, okay? So the loss is still quite high, okay? So it has a high loss. Now, this is basically articulated here. So it's true for the training set, so which should suggest that the problem relates to training the original network. So the original network is not well trained, rather than a simple failure to generalize to new data. So now if I ask you guys, and this is very important, if you're training a neural network and you want to, or you're comparing different neural networks and you want to know whether your network is it struggling to learn or to generalize, you need to do these two plots, okay? So if your network is struggling to learn, you would actually expect it to be not really good at generalizing, okay? So this will affect the generalizability power or capacity of your network in a negative way because your network has not been trained well. But if you look only at, you start only with, the generalizability, the test set, the test error, you cannot actually know if this is because of the distribution of the test set. The distribution of the test set may be shifted from the distribution of the train set. Okay, so it could be a problem of distribution of data, fracture or domain shift, and you may not really understand why you have this gap right here. So to gain a deeper understanding, this is what you need to look at, and this is the right question to ask. How do my 26-layer and 20-layer networks behave when they are trained? Okay, cool. Now, this is the first issue. When the network becomes deeper and deeper and deeper, somehow the loss becomes harder to optimize. So the loss is harder to optimize. Okay, so why is that? Why we have this? So how can we gain a deeper understanding of this behavior? Now, we observed from the observation, from this observation, how can we derive some conclusions, or maybe how can we drive new experiments or hypotheses that allow us to understand what's really going on? So if we look at the loss, you guys remember, first we look at the loss function. Okay, so this is our loss. L of W, and we want to find the optimum. And to find the optimum, we actually need to calculate the gradient, and the gradient of the loss is actually calculated before we use any batching. It's calculated at each point x of the data xi. Okay, so this is L that is parameterized by W. So W is fixed, so we're going to evaluate this. So at W, for example, T, and then for these parameters, we're gonna measure the loss at each point. So the gradient of the loss, we have seen that the gradient for each point may have, one direction or different directions. But the idea is that if the loss is hard to optimize, it could be different things, okay? So maybe there are two things here that we need to think about, okay? So why my loss is hard to optimize? There are two words here. The first word is loss. The second word is optimize. So the first word is loss. I need to look at the shape of my loss. Okay, is it smooth? Is it, kind of, zigzaggy? Okay. And so smooth, it means I have a loss like this. So for example, it's easy to optimize. Okay, so I'm going to redraw it. So something like that. Zigzaggy means my loss is really horrible. Like it's so hard. We have narrow valleys here. It's so difficult to find an optimum. It's not smooth enough. The optimize is about the gradient descent, okay, the gradient magnitude, okay? And also we have the gradient magnitude because it's so important. The gradient magnitude, it affects the update of my parameters. Sorry, we have eta, and this is the gradient of the loss at t minus 1, okay? So here basically, let me write it better. Sorry, guys. WT minus 1. Okay. So here it means that the gradient is not that good. So the gradient, if the gradient is too big, if the gradient is large, then I'm going to jump from 1W. So if this is, for example, my loss, okay, LW, and I'm iteration. So if my gradient is large, I'm going to go from here to there, right? And then I'm going to jump over. So I'm kind of, I'm taking big jumps because I go from WT to WT plus 1, the next one, for example. And this jump is actually controlled by the magnitude of this mathematical element over here. So it could be that my gradient is too large, so I'm jumping all over the function. So here, I'm taking a big step over there, right? So it's kind of going everywhere, and we cannot find the optimum easily. It could be also that my gradient is too small. So if my gradient is too small, it means I can barely move, so I am stagnant. So if the gradient is so small, it means I start from here, and I go like an epsilon over there, and the change between WT and WT plus 1 is so small that I'm barely moving, so it's going to take me a long time to converge. So basically, you need to think about two things here. You need to think about the shape of the loss of the function, okay? So the L as a function of W, and here the L of W, the value of the L as we iterate. So so here is also, sorry, so the iteration is a different thing. So I'm going to put here what I actually draw is L of W as a function of W, okay? So, and the gradient, the change in the loss. So these are two things that may explain why our gradients our loss is not easy to optimize. And this is based on just simple gradient descent optimization fundamentals of machine learning, okay? Now let's look at the second, so this problem. So we're gonna go deeper into this issue. So the second issue is that not just the depth. So the depth is a problem. We have another, issue that arises, which is the issue of shattered gradients. Okay, so everything is shattered. So let's see what shattered gradients, what this actually means. Okay, so shattered gradients, this problem, it arises because of the changes in early layers. So the changes in the early layers, which are quite big, they modify the output in an increasingly complex way as the network deepens. Okay, so as the network becomes deeper and deeper and deeper, right? What happens is that the gradient of the changes with respect to the first layer, okay, becomes really it becomes more complex at this change. The change in the first layer affects the change in the second layer, affects the change in the next layer, and all of these changes are actually changes in weights, right? So it's the changes in the weights that we want to find. We want to if you go also to grade, if you look again at the formula of the gradient descent, which explains everything, which is a beautiful formula, I love it. So if we write it this way, minus eta, the learning rate, times the gradient of the loss at WT. Okay, now we can write it in a different way. We can just do this actually change. T plus 1 minus WT is equal to negative, I should not forget the negative eta. So it's the opposite direction of the gradient. That's why we called it descent. And here, this defines a delta W at, we can say at, T plus 1 here, okay? So this change in my weight, the change that I want to incur, what is the delta that I want to learn in such a way that when I'm changing my weight in this layer, okay, I will get a better H1 and an H1 here. I induce then the necessary change of the weights in this second layer, that I'm going to get a better H2, etc., H3, until we get H4, which is, our final prediction. So the idea here is like, I'm trying to learn. So this is important. I'm trying to learn the right delta, the right change that I need to discover or apply to my original W0, my random initialization. How can I change this by a delta in such a way that if I pass this over sequentially, if I pass the original signal sequentially through all these weights and mappings, okay, and biases, with, of course, activations, in between, we're going to get the Y. We're going to get the exact value. So what is the change? And it's all about this delta. Like even when you guys are learning as a student, let's say, you have, for example, I'm going to write here. So let's say you are starting from here and you see yourself in, so I'm going to put it, so let's do F1. F2, F3, for example, okay? So you have a future memory of yourself. So you want, for example, to become, successful in AI. You want to become one of the masters in AI. And this is your goal. So you want to generate this in you, okay? So for you to be able to basically generate this outcome, so this is you right here, okay? So for you to be able to generate this outcome after some time, what you need to do, you need to reverse the problem. So you need to think about the consecutive changes that you will induce over time and over years for you to be able to achieve this. And if your path is optimal, if this path is optimal, maybe you can have a better path. Let's say this one, okay, it's optimal. Then you will get really closer to your final output. So what does that mean? It means that even in terms of personal development and personal improvement, it's about your delta. The delta one I'm using here. What is the change? What is my improvement, sequential improvement? The first delta one, the second delta two. I'm moving from one level to the next level. and then delta 3, etc., until I get there. So you can look at this or think about this as a reverse problem, as I mentioned earlier, where you're trying to reconstruct this backwards through back propagation using gradients and changes in the weights that you want to induce through your losses, right? By going step by step and doing the gradient collection as we have seen in back propagation. And as you identify, you calculate your gradient properly. As I mentioned, from the gradient, you can easily identify the delta and the weight, your delta that you want to get, the change that you want to induce in yourself to be able to reach your goal after some time. Okay, so this is a bit philosophical, but it applies to this beautiful architecture. And here, if we look at this, we have a problem right here. So if you want to, if I ask you right now, okay, so if you want to have a successful, groundbreaking company in AI and you want to build that within the next 5 years, and I ask you, give me your attributes. So tell me all the features you have right now. So for example, you've taken a few courses that you, passed successfully, you aced maybe, you have a few projects, you have some, reading diet, you're kind of doing some networking. So all of these, we will quantify all these features. And then you'll tell me exactly what are the, what is the desired output. And then when I ask you right now, and if you guys take a moment and I ask you, can you build this trajectory? Can you tell me exactly in year 1, year 1, 2, 3, and 4, which exact delta in those features, the original features, because these are what we want to perturb, right? So remember, our W belongs to RD, and RD, D is the dimension of the original features or the measurements that you hypothesize that they are important for you to be able to predict your goal, okay? Or generate your goal. So now if you think about this problem and I ask you, can you guys identify your delta in the number of projects, the quality of the networking, the breadth of the networking every single year? Okay, so now you're gonna sit down, probably spend the whole day trying to come up with all possible pathways that will get you there. So you will start with a path like this, and then you're trying to optimize. You say, no, I've read a book or I watched a vlog that shows me that actually the problem is more complex than that. So you have a lot of things to cover, and you may not be able to find the optimal path. It's actually so difficult to break. It's difficult to break down a problem backwardly or reversely. So it's not just the breaking down that is actually the most difficult task. The most difficult task is actually identifying the sequence of optimal changes to implement along the way, okay, the way from X to Y. So you need to get all these changes, delta 1 until delta n, that will get you from your X to your Y. This is really hard, okay? And finding an optimal way is not very obvious. Now let's get back to our problem. So here we talked about shattered gradient. So what are those? So before I explain this problem, there is basically, the idea here is getting a bit closer. So we said that we needed to identify the change, okay? So this change, when it happens in the early layers, it actually will affect all other layers. We see that in the chain rule of derivatives. So let's look at the change of the final output, which is H4 or Y, okay, with respect to F1. So let's see here how F1, okay, the first layer, how the final output changes with respect to the first layer F1. And when we write that, we can use the chain rule in here if you guys express it. So we need to backprop basically. So it's sequential. So you express y as a function of f4. So here you go, from y to f4, f4, f3, because f4 depends on f3, f3 depends on f2, f2 depends on f1, and this is how you actually get the df4, which is actually dy df1, okay? So you guys can see now through this beautiful chain rule that if you have any issue, if your gradient breaks at any layer, okay? So if the changes in layer F3 with respect to layer F2 becomes close to 0, this guy will become close to 0, okay? So you can see that through this chain rule that it is a multiplication of consecutive dependent, codependent changes from layer to layer. And this will propagate. So anything that happens in F1, it will propagate through to from F2 to F1, F1 to F2, 2 to 3, 3 to 4, and this is only with F1. So if you look at this side, you may think, oh, my y depends only on this guy, but this guy affects all other guys. Yay. So that's the chain rule. This guy affects everybody. So if I basically get something here, it will override or overrule everybody else. It will control all the subsequent changes in all layers. So if we go back to our example, what this tells us in the self-development example that we have here is that the first year where you're going to do the hardest changes, okay, this year will determine and will control all subsequent changes in the coming or follow-up years. So what does that also mean? It implies that I really need to be careful about my choices in the first year, because this year here, according to the sequential model, remember guys, it's sequential. We're not residual, we're sequential. If we follow a sequential model of reasoning, I need to be careful about the choices I make here. I need to be careful about the delta I induce in the first year, okay? Because it will propagate through all other years. And it's the same. So from 1, it propagates to the last one. Then from 2, it propagates to the last one. 3 to the last one, okay? But the most important one is the top one. That is very important, okay? So now let's look at this problem. So what happens when we do this? So basically what this formula is telling us is that, let's choose a different color, that a change in the parameters of F1 propagates, okay, this changes to F2 all the way to F4, the very last layer, which means the gradient at each data point may be different, okay? So which means that, at each data point, as I train this network, because, these changes propagate faster to the last layer, then I may end up with completely different gradients, okay, and different parameters, because we have different parameters between different points. The parameters or the W's will change. The W will change, the delta will change, my gradient will change faster, and then the problem is that I will end up with, different directions of my gradient for 2 points. So if I have, for example, this is my data set, and I have x and x prime, and I calculate the gradient at x, and x prime. So these will have maybe completely different directions, although these are, consecutive points in my data. So I go, for example, I go from this one to the next one, and what happens is that my gradient is changing. So my loss function shape is changing between 2 consecutive points. So something is kind of happening, like a change in shape of my function. And this is also impacting, of course, the change in the parameters that we want to update. So now this phenomenon is called shattered gradients. We call it shattered gradients. because you end up with gradients that are shattered and that have completely different directions, and they are scattered, okay? So let's look at this example. Let's look at a real example, a real data set, and see what actually happens. So first we have here, we have a plot, and in this plot, we plot the gradient of the output with respect to the input, okay? And we have the input x. So in this example, what do we have in this example? So here we have a shallow network with 200 hidden units and what we call a Glord initialization. So I won't go into the details of this initialization. This initialization basically is based on the he initialization, and the head initialization is the way we want to initialize our parameters W's across all layers, W1, 2, 3, 4, bias 1, 2, 3, 4, okay? So the head initialization, it initializes the biases beta to 0, so all biases are set to 0 at the very beginning of the optimization, and it samples W from a normal distribution centered around 0 and of standard deviation of 2 by DH, where DH is the number of hidden units and the previous hidden layer. So basically you're normalizing. So if you're dividing by the number of hidden units in the previous layer. So if you have a very wide layer compared to a very narrow layer, okay, so these are the number of neurons, then you're going to create here a normal distribution that is, so it's so wide, so it would be very narrow, and because you're dividing, and this will be slightly wider. So this is the normal distribution that we create using this initialization. Of course, you guys, well, maybe we can read this paper together. It would be interesting to understand exactly why they have this hypothesis and what it means and how they rationalize it and how they came up with this exact number, okay? But the idea here is that this head initialization is really good. It helps the network to be trained well, okay? So that's the main idea. So now we start with that, and you can see that with 200 hidden layers, the gradient here of the scalar network, output y with respect to scalar x, so it's these are two values, a simple network that maps, scalar inputs into scalar outputs. And we have the changes, like the gradient changes slowly as we change the input x. So you can see here that this is not a very abrupt change. It's kind of slowly, and then you have some leaps over there. And as you change the input, as the values vary here, you have a gradient that is, slightly decreasing. So you can fit a linear curve over here. It's not too bad, actually. Okay, so it's not something exponential. It's something quasi-linear or linear somehow. Okay, so something maybe like this. All right, now let's look at the next example. So the next example now, we have not one single hidden layer. We go from one hidden layer to 24 hidden layers. So we have increased the depth of our network. And we are still mapping a scalar input x onto a scalar output y. So x could be, for example, the age of a person. Y could be the IQ of a person. So it's just, two random numbers that we're trying to map one onto the other. And what do you guys notice here? Very interesting behavior, right? So the gradient here, dy dx, the output, the change of the output with respect to the change in the input is completely kind of scattered. It is zigzagging, it's going up and down, okay? So it's not stable at all. It's kind of, zigzaggy. It's, something that is a bit chaotic, not too chaotic, but there is a pattern here, but it's kind of, not stable at all right? So you can see it right here. And this is because of the depth. We increase the depth from 1 to 24. Now let's look at the last example. So in this last example, C, we have, what do we have here? So here we calculate something interesting. So we calculate the correlation, okay, between the gradient and the change, in the output. So we're actually calculating the correlation between the signal dy dx and the delta x, the change in the input. So what we want to see is how does the gradient, okay, so if you look at the original, the first layer where you have the x, as we change the input, so as we go from, so this is, the first x, as we go from a point xi to another point xj, right? What happens to our network right here? So all of this is our network, and then we have a final output y. So what happens here? So we want to see the change xi minus xj. This is the delta x. And we want to look at how the changes in the features of our two consecutive training points, they affect the the changes in the gradient. And this will tell us how stable our gradient is. Like, does the gradient get affected and completely changed by points? So this will tell us if 2 points will have similar gradients, or different gradients, because we're calculating their differences and the correlation between the difference in their gradients. Okay, so what we notice here, first, when you use 2 hidden layers, so this is 0, this line, in the middle, it strikes a 0. So let me maybe zoom a little bit. So this strikes a 0. So here we have our 0 autocorrelation, which means nothing is they are not correlated anymore. They're completely decorrelated. So when you start with 2 hidden layers, you have a very nice correlation. 1, it's perfect. Okay. Now you go and you increase the number of layers to 4. It starts kind of linearly decreasing. You get to 24 and it's 0 correlation. So the gradient, the shape of your loss, the shape of your descent doesn't depend at all on your data distribution or changes in your data, like statistics or your data basically features, okay? So they're completely uncorrelated. So the network here is not making sense that out of these changes. So it looks at a dog here, at a dog there, it sees that the change here is small, but the gradients are all over the place. So it's not learning any patterns. It is failing dramatically, okay? That's not good news. So here, what this tells us is that what I just explained. So for a deep network with 24 layers and 200 hidden units per layer, so 200 times 24, right? So these are the number of total units. This gradient changes very quickly and unpredictably. Okay, so that's for the B. Now for the C, the autocorrelation, so that's for the B. So see here, it's like unpredictably because it goes up and down. So it's actually kind of chaotically. And then for the C, the last plot, the autocorrelation function of the gradient shows that nearby gradients become unrelated, okay, for deep networks. So which means that if 2 points, nearby gradients, if 2 points are actually similar, their delta is similar, we don't have similar gradients anymore. And these gradients become completely unrelated. So if they are similar, they would be something, maybe we'll have something like this. Okay, so these are similar gradients. They're correlated. Now they're pointing to the same direction. And if they are completely dissimilar, they will point out, let's choose a different color. So they will point out towards completely divergent directions, okay? So these are different gradients. So the shattered gradients phenomenon may explain why it is hard to train deep networks. And here, gradient descent algorithms, they rely on the loss surface being relatively smooth, so the gradients should be related before and after each update step. So basically, we hypothesize that the loss is smooth, but it turns out that maybe the loss is not smooth anymore, because here you can see that the gradients change abruptly up and down. And like, when you do also different points, this is a loss at point X. When you calculate the shape of the loss at point X prime, what's going to happen here? So these are 2 points. You're going to end up with something very different. So up, down, maybe, and then you're going to go up, like down like this, okay? And then having very completely opposing shapes, right? So when one is going up, the other one is going down. And you can see that these guys actually, you know, they may induce very random kind of shapes. So you'll end up with something that could completely messed up, okay? So now these are two losses. As I explained, that this is a loss. This is the loss measured at x prime, and this is the shape of my loss if I visualize it at only a point x, training point x. Okay, so now we can see that, you know, sequential learning has so many hurdles. You know, getting deep is a problem. We have the problem of shattered gradients. We have also, you know, it's hard to train, it's hard to learn, and we understand now, we have some insights why that happens. Is because of these gradients and because of the shape of the loss. As I mentioned here, two factors: the shape of the loss and the magnitude and the direction of the gradient. All right, now let's look how we can solve this problem. And we will introduce in a bit residual networks.